assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have a wire loop with 50 turns that is experiencing a changing magnetic field over time in these three different intervals here, 0 to 3 seconds, 3 to 6, and 6 to 9. And what we want to know is, given that this field is uniform everywhere and always parallel to the normal of our loop, we want to determine what the induced EMF is during all these time periods. And we also want to figure out what the induced current is in our loop, given that the wire has a resistance of 0.5 ohms. So we'll start off with the first period here. We'll number these 1 through 3. So for the first period, we're just going to start with the fact that the induced EMF is equal to minus the change in flux over the change in time. And this is just known as Faraday's law of induction. And if we're dealing with n loops, then that'll be accounted for in our flux here. And if not, we can just tag an n to the outside of this induced EMF here. So we will add an n times the change in flux through a single loop over the change in time. Okay. So our change in flux from 0 to 3 seconds is going to be equal to the flux at 3 seconds minus the flux at 0 seconds. So the flux at 0 seconds is going to be 0 because we have a magnetic field of 0 teslas at that time. And then the flux at 3 seconds is just going to be equal to the magnetic field at 3 seconds times the area. And normally we'd say times the cosine of the angle between the field and our surface normal. But at the start of the problem, we said those are always going to be parallel to each other, so we don't have to worry about the cosine in this case. So this should just be equal to the magnetic field at 3 seconds times the area of our loop. Which is going to be, times n. Or sorry, once we add it all in, we'll do the times n. So then our induced EMF from 0 to 3 seconds is just going to be minus n times B3A over delta t, which is just 3 seconds. All right. So if we plug in all our values there, n is 50, A is 0.15, and B is 0.4 teslas, we will get that the induced EMF is minus 1 volt. Okay. Now for the second EMF, for this one, we can see that the magnetic field stays the same during the entire period. So since there's no change in the magnetic field, there's also going to be no change in flux because we aren't changing the area or the angle or anything else like that. So if there's no change in flux, then the induced EMF is just 0. So the induced EMF from 3 to 6 seconds is just 0. And similarly, I said we're also going to look into the induced currents for this problem. But since we know for this loop that there's no induced EMF, we can just get the current out of the way right now and say that there will also be no induced current, since there's no induced EMF. And we'll come back to the other currents once we find our last EMF here. So again, for our last induced EMF from 6 to 9 seconds, we're just looking at minus n times the change in flux from 6 to 9 seconds over delta t, where now our change in flux from 6 to 9 seconds is the flux at 9 seconds minus the flux at 6 seconds, where the flux at 9 seconds is going to be the field at 9 seconds times the area. We'll just say B9 times the area, minus the field at 6 seconds, which is B6 times the area. Or, if we want to plug those in, we know that the field at 9 seconds is going to be 0.2, and the field at 6 seconds is going to be 0.4. This would be 0.4 times A minus 0.2 times A, which is just 0.2 times A. So our induced EMF then is minus n times 0.2A divided by 3 seconds, which, if we plug in our remaining values for n and A, is just going to yield 0.5 volts. And back here, these were mixed up. This should have been 0.2, and this one should have been 0.4. So then we would have a minus 0.2, which will cancel out our sign, and we'll end up with a positive induced EMF. Okay. So now, for calculating the induced currents, we're just going to refer to Ohm's law, which says that the voltage drop across a resistor is just going to be IR, or in this case, our voltage is just our induced EMF. So E equals IR instead of V equals IR. And if we divide both sides of that equation by R, we'll have I equals E over R. So we'll just plug in our resistance and our EMFs for the different periods we have. So since we're right here, we can figure out the induced current in the 6 to 9 second period, which is just the induced EMF in that same period divided by our resistance, which our resistance was 0.5 ohms. And if we put those numbers in, we will have 0.5 over 0.5, which is just 1 amp. And similarly, if we did the exact same thing for our 0 to 3 period, we would have minus 1 volt for our EMF in the 0 to 3 period, divided by 0.5 ohms, which would just be minus 2 amps. All right, so we determined the induced EMF in our loop here for 3 different periods in which our current is changing. And by using our calculated induced EMF, we were also able to determine what the induced current is in our loop at any given point in time.